Hello, hello, and welcome back to CS 500 Design and Analysis of Algorithms. Today, we're in chapter 9, talking about parallel algorithms. Again, with emphasis on algorithms and their analysis, as opposed to parallel programming, which is an important subject, but not the focus of the present lecture. Let me start by sharing the slides. So what you see here is the outline, the overview of chapter 9, parallel algorithms. We start with a classification and overview of different aspects of parallel algorithm and analysis. Then we will give some examples, namely the important parallel prefix algorithm, or more precisely, circuit for parallel prefix. First, with a specific example of parallel maximum calculation, and then its generalization to arbitrary associative operation. We'll apply this in various different settings. So this is again one of the benefits of abstraction, having generalized from maximum to arbitrary associative operations. One of these associative operations will be Boolean disjunction, which will allow us to devise a very efficient log-square time parallel runtime algorithm for graph reachability. We will also apply the parallel prefix method to another associative operation, which will allow us to predict carries and thus accelerate adding binary numbers to logarithmic parallel time. And finally, we will recall and continue from introduction to algorithm, a discussion of parallel sorting networks. Again, we emphasize that this is just a small aspect of the huge field of parallel algorithm. This is just one chapter out of 10 chapters in this course. And its purpose is to give you a taste and open a door and give you a small overview of the huge field of parallel algorithms and its contemporary research topic. So let's start with the first part about classification. So what you here see is a data center. So there are like thousands or maybe even 10,000s of computer racks, each one containing maybe even several PCs, ordinary PCs, each PC in turn having maybe several CPUs, and each CPU having maybe several cores. And these can be run either individually or combined into a huge distributed computer system. This is nowadays a typical way of how distributed and parallel computing on a large scale proceeds, as opposed to maybe the late 80s, 1980s, when parallel computers were dedicated hardware devices like, the famous Cray computer architecture, which was really essentially one computer dedicated and built for parallel computing. Here we have general purpose computers combined together, off-the-shelf computers. So this is a kind of a large-scale parallel computing or coarse-grained parallel computing. At the other end of the spectrum, there's fine-grained parallelism, maybe even down to individual gate levels. This happens all the time in your computer, in your CPU. Here is a simple example where 4 input signals and these 2 inverter gates operate in parallel simultaneously. invert signal A and C. In the next stage, so after one clock cycle, these two gates, one conjunction and one disjunction OR, operate in turn and simultaneously processing the negated or unnegated input. And the next stage, we have a disjunction and a conjunction working simultaneously, and finally the output is produced by a final logical OR. So here we have 1, 2, 3, 4 stages, and yeah, kind of small parallelism, always at most 2 gates, but you can imagine that you can also have like 4 gates here, right? So 1 here with 2 inputs. This one has 2 inputs. So the number of inputs on each level can at most double looking back from the output, from the result. So that is something we will recall in the next slide. But this is a kind of micro-parallelism, fine-grained parallelism on the gate level. Now, from the perspective of actual parallel computing, there's of course a huge difference between both in terms of how much effort has to be put into designing parallel parallel circuits, different approaches. Here we have to distribute data, but asymptotically, the difference is arguably only a constant factor. Let me just imagine having one PC for every gate here. So one PC only executing this gate and another simultaneously this gate, passing on the data to this and to this in turn, and so on. This is, of course, a highly inefficient way of using these computing resources, but asymptotically, the slowdown of doing so is only a constant factor. And conversely, every PC is already such a complicated logical circuit, and combining all these together results in one huge logical circuit that different PCs and their circuits operating simultaneously. So essentially, both from our perspective up to constant factors are the same, interestingly. Another aspect beyond this distinction between fine-grained and distributed computing is how the data is presented and how the instructions are presented. On the one end of this spectrum, we have single instruction, single data. And on the other hand, we have multiple instruction, multiple data, and combinations between them, multiple instruction, single data, single instruction, multiple data. And the difference is do all CPUs, all processors execute the same code, like here in this example, or does every processor get its own individually tailored piece of code? Do all processors operate on the same data, or is the data kind of split and distributed to each processor individually, and the combinations between both? A final type of classification is pertains to the PRAM model, which is one model of parallel computing, a model where we have many processors, but only one memory pool. So this is kind of a example of multiple instruction, single data. Arguably, it's not entirely realistic that hundreds or even 1,000 processors can access the same memory simultaneously. This technologically would create a bottleneck, but for the purpose of algorithm design and analysis, it's a popular and convenient model. But also in this model, there are some nuances and details to observe when designing algorithms, namely what happens if two processors access the same memory cell. Arguably, if two processors want to read from the same memory cell, that could be considered as resulting in a collision and could result in an exception and the program being considered invalid whenever that happens. So it's the programmer's responsibility to prevent the processors from accessing the same memory cell simultaneously. This is the case for the exclusive read, exclusive write variant of the parallel random access machine. At the other end of the spectrum, there's a concurrent read, concurrent write parallel random access machine where different processors are allowed to access the same memory cell at the same time. And when they read concurrently, there's not much doubt about the semantics. They just obtain the same value as currently stored in the cell. But when two processors want to write to the same cell simultaneously, then there's additional question of what is the semantics of a concurrent write? So for example, if they both write the same number, then at the end, the memory cell will reasonably be said to contain that same individual number. But what happens if they write two different numbers and their variance, let's say this so-called priority PRAM, where the processor with the smallest index gets priority and the value of that processor gets written into the memory cell and the value written by the other processor is ignored. And other variants of the PRAM model say in such a case, if two processors want to write different numbers to the same memory cell, this is prohibited. This will throw an exception. It's a programmer's responsibility to prevent that from happening. So there are subvariants of the concurrent read, concurrent write PRAM. And there's also an intermediate variant, concurrent read, exclusive write, where two processors may read the same memory cell simultaneously, but writing is only permitted to one processor exclusively. And when that processor writes, no other processor may read. So these are the variants of PRAM models. And as I mentioned, parallel algorithms is a huge and flourishing contemporary field of research. In this chapter 9 of the present course, we can and will, of course, only address some aspects, give you a taste and make you maybe interested in pursuing this direction of research yourself. And we do so, again, following our virtue of focusing on algorithms, not on programs, and also making heavy use of the power of abstraction, devising general algorithms, or more precisely, we're going to devise circuits, and then applying them to specific examples, such as the aforementioned carry look-ahead adder for adding two binary integers in logarithmic parallel time. Okay, so let's start with some example circuits, and we often will draw the circuits not from left to right, as in this example, but we will draw them in a sense from bottom to top, like a tree, or more generally like a directed acyclic graph, and these graphs will be organized in layers, so it corresponding to the kind of clock cycles. And notice that in these circuits, every gate kind of operates and fires only once. That's very different from distributed computing, where like several CPU cores. Of course, each core executes an entire sequence of instructions. Typical or characteristic for a, circuit is that every gate operates only once, and then kind of the operation proceeds to the next stage. And these, from then on, these two gates, for example, will remain dormant. And I'll get back to that subtle distinction in a few minutes. So long story short, in this chapter 9, we focus on circuits as a model of parallel computing. And in this model, parallel runtime is formalized as depth of a circuit. So for example, here, this circuit, this tree, has steps 1, 2, 3, 4. Here are the inputs, here is the output. So the parallel runtime would be considered counted as 4. As in general algorithms, we do not focus on absolute running time, but we count not number of operations, but we count number of stages, or more precisely, the levels in such a circuit, in such a layered, they say, acyclic directed graph. Here's another example of an abstract circuit. This is actually maybe similar to machine learning, which is not at all our topic, but it illustrates another case of a layered directed acyclic graph. Input layer, first layer. After first layer is finished, the second layer operates and the first layer remains dormant. Then execution proceeds on and so on until the final layer, and then the output is produced. And you see here that in general, circuits also can have several outputs, not just one, but several outputs. And following our convention, we may occasionally draw it in that way so that the execution proceeds from bottom, from the leaves, upwards to the root, or the roots, several roots with the output. So depth is our measure of choice for parallel runtime, but another important measure is the size of such a gate. So the size is counted as the number of gates, the number of nodes here in this directed acyclic graph. And we will usually only allow binary gates. This is called fan-in-2 case, bounded fan-in. Research also considers unbounded fan-in circuits, but this, in order to make these realistic, unbounded fan-in, like n-array, 100-array Boolean disjunction, has to be boiled down to a combination of binary gates, binary disjunction, binary ORs, as we will see on the next slide. So this is our two main measures of cost, and it also clarifies, according to our virtue of computer science, the primitives that are used. Namely, the primitives will be binary gates, various types of binary gates, for example, logical binary gates. Now, if we're considering parallel computing beyond circuits, such as the aforementioned PRAM model or models, different notions of size and parallel runtime are employed. So parallel runtime for distributed computing, where every computer, every core, every CPU operates, executes a sequence of instruction, not just once as in a circuit model. Their parallel runtime is called the span. Span is the longest runtime of any of the cores, CPUs, or PCs involved in the computation until also the last one has terminated. And in this case, the size of such a parallel algorithm accounts not the number of gates, but the number of cores, the number of CPUs, the number of PCs employed in the computation. And in distributed computing, also communication becomes essential, particularly communication volume, which is kind of happens implicit in the circuit model on these edges as the data processing proceeds from the leaves bottom up to the root top. This kind of distributed parallel computing is the so-called work. the so-called work then amounts to the span, the longest parallel running time, times the number of CPUs involved. And this is called work because if one were to simulate such a parallel algorithm on one single sequential computer, it would maybe simulate the first CPU, then the second CPU, and so on, and then repeat for the first instruction, and then repeat for the next instruction. And so to simulate all CPUs throughout their entire span sequentially, this is kind of the running time that a sequential simulation would take. And I mentioned this because it's an important aspect of Brent's principle, which we will see in just a minute. But first, let's recall that in the sequential realm, time refers to the sequential running time, the number of operations executed by a sequential algorithm. And in this chapter, we will actually use the notion time to refer to the optimal sequential algorithm. So when we consider, for example, sorting, then the sorting problem, then the time, sequential optimal time for sorting is n log n, as we know. So here in this chapter, time will not refer to an algorithm, but it will refer to the optimal time of a problem. And then the speed up that we obtain by designing and analyzing a parallel algorithm is defined to be the ratio, the fraction, optimal sequential time divided by the depth, that is the parallel runtime of the parallel algorithm that we designed. So let me say it again, time refers to the problem, not to a particular algorithm. Depth refers to the parallel runtime of the parallel algorithm that we want to design. And the speed up compares how much faster we are with our particular parallel algorithm compared to an optimal sequential algorithm. And Brent's principle says that the work is always greater than the time that is the running time of an optimal sequential algorithm. Or in our circuit setting, Brent's principle says that the size of a circuit is always greater or equal than the sequential optimal running time of a sequential algorithm solving that problem. Work and size refers to particular circuits or particular parallel algorithm. Time refers to number of operations executed by a hypothetical optimal sequential algorithm for the problem. And the reason, or the justification, if you like, the informal proof of Brent's principle is that if we were to simulate this parallel computer sequentially, then this is roughly asymptotically the number of instructions executed by our sequential algorithm simulating that parallel computer on sequentially. And by the definition of time, time being the runtime of an optimal sequential algorithm, this sequential simulation must be greater or equal to the running time of an optimal. And similarly, if we simulate our circuit on a sequential computer in so-called topological order, first executing this gate, then this, and then this, so on from the input, then proceeding to the next layer from left to right, let's say, and the next layer from left to right, and so on. Then this is a hypothetical sequential algorithm simulating this circuit. And again, this particular sequential algorithm cannot be faster. It will be take at least the running time of the optimal sequential algorithm by the definition of time referring to the optimal sequential algorithm. So this inequality is called Brent's principle, and it's very helpful in proving parallel algorithms optimal. Remember, one of the virtues of computer science was to not only to devise and analyze algorithms, but also to prove them optimal. We proved, for example, comparison-based sorting to be optimal with running time n log n. Now, how can we prove a parallel algorithm to be optimal? And here, Brand's principle allows us to do that. So, for example, if we were to devise and analyze a parallel algorithm for sorting, whose work is n log n, then we know from Brand's principle that this is going to be asymptotically optimal, because then this inequality becomes at least asymptotic and equality compared to the n log n for the optimal sequential algorithm. Similarly, if we design a sorting circuit, circuit for sorting whose size is equal up to constant factors to n log n, then we know from Brand's principle that this is going to be asymptotically optimal, because we cannot have work or size asymptotically less or equal to the time, less than the time. So that's one way of proving parallel algorithms or circuits optimal with respect to their size. But of course, we're also interested in parallel algorithms that are optimal with respect to their parallel runtime, with respect to their span, with respect to their depth. And here, another principles come in, but let's first recall another important measure, and that's the overhead. The overhead basically says how far are we off from the optimal according to Brand's principle. So the overhead is the fraction size divided by time, right? So if we have size asymptotically equal to time, then this ratio will be a constant. And that's as good as we can get according to Brand's principle, but maybe we're off. Maybe our size is much larger than the optimal feasible according to Brand's principle. Then the overhead will be maybe n or n squared. So this is a measure of how far we're still away from optimum according to Brand's principle, and that's an indication that we maybe should start over designing and analyzing a better parallel algorithm. As I said, this refers to the optimal size of parallel algorithm, but we're also interested in optimal parallel runtime, meaning optimal depth or optimal span, depending on circuits or distributed computing. And here, the following lemma is helpful in proving depth optimal. And the observation, since we're talking about circuits of binary gates, meaning directed acyclic graph with of valence 2 of out degree 2, and any such binary tree or binary directed acyclic graph can have at most twice as many gates on the next level as previously, going down now from the root, not up, as our execution proceeds. And if furthermore such a circuit depends on all of its inputs, if there are no unnecessary inputs that are ignored for the output, then first observation, such a circuit must have size at least n. Well, every input must be somehow processed, must be enter some gate, otherwise it's superfluous. And second observation, the depth must be at least log n, because the number of signals looking back from the root backwards can double, at most double in each stage until arriving at the leaves where the inputs are presented. So put differently, if we were to design a parallel algorithm or a circuit for sorting, and this circuit has depth log n, then this is going to be optimal depth. And similarly for many other problems that we're going to consider, our goal will be to devise circuits of logarithmic depth, because then this is going to be optimal parallel runtime according to this lemma. And let's start with one such first such example, namely calculating the maximum of n numbers. Okay, so here's a formal specification of a problem. Input are n numbers, or more generally n elements from a totally ordered set, and the output is the single number, the maximum of all these capital N many inputs. Here's a depiction of a circuit, namely the leaves. This is where the inputs are presented. In this example, 16 inputs, so capital N is 16. And as I said, the underlying the data can be numbers, but as we're aiming for generalization, let's consider a totally ordered set, as we did when we talked about sorting. Now, what are the primitives according to our virtue of computer science? The primitives that we may use is a binary maximum operation. So not here, this is an n-ary maximum, and we want to express the n-ary maximum using a combination of binary maximum operations. So fan in 2 only to simulate fan in capital N. Let's recall what is the optimal sequential time for this problem. Sequential algorithm will maybe take the maximum of the first two elements using one binary maximum, take the result and calculate the maximum of that with the third element, take the result and calculate the maximum with the next element, and with the next element, and so on, so that the trivial naive algorithm going through all elements in a loop and always introducing the next element to the previous tentative maximum. That's a obviously optimal linear sequential algorithm, so that the optimal sequential time for this problem is O of n, and observe again that here in this model, we're ignoring the magnitude of the data as we did for sorting. We just count the number of binary maximum operations. So this quantity will be O of n in our case. And now we want to reach that. We want to design a circuit whose size is as close to O of n. So more precisely, we want to have small overhead. We want to have also linear size of our circuit, but we also want to have logarithmic depth. And the way to do that is kind of obviously is to construct a binary tree, calculate the maximum of these two elements and simultaneously of these two and simultaneously of these two. So we put the binary maximum into each of these nodes of our circuit, and then we will proceed one layer up, having reduced the magnitude, the number of data items by a factor of 2 in each level. So after logarithmically many levels, there's only one data item left, and that's going to be the result, the maximum, so that this binary tree is a circuit for calculating the maximum of n data items with a huge parallelism. So the size of this binary tree is O of n, or more precisely, it's 2 times n minus 1, as you know, holds true for any binary tree. So this is optimal according to Brenn's principle, because the sequential optimal algorithm had linear running time. That's good. And the depth is logarithmic, which is also optimal according to the lemma that we had on the previous slide. So that this is an optimal circuit for expressing the n-ary maximum using a combination of binary maximum gates. Good so far. Our first example is complete, and yeah, let's calculate the speed up by comparison with the sequential case. The speed up is n divided by depth log n, and the overhead is constant. So this is optimal. And we're ignoring the magnitude of operands for now, but as usual. Now, what other operations can this kind of circuit calculate? Observe what really matters here is not that it's a maximum we're calculating. What matters is only the property of being associative. We're kind of putting brackets here, right? So we have these 16 items, but we're putting implicit brackets between these two, implicit brackets between these two, and brackets between these four. So we're kind of rearranging it. We're not changing the order. Order would require commutativity, which is true for maximum, which allows us to maybe flip x10 and x9. But that's not what we're doing. We're exploiting the associative laws. And therefore, these considerations immediately apply as well and generalize from the case of a totally ordered set with a maximal operation to the case of a set equipped with any binary associative operation. And calculating the n-ary operation of this variant of this operation. For example, adding is an associative operation. So this plus with a circle, placing by axial addition. Multiplication is an example. Disjunction, logical disjunction, conjunction, many operations are associative, and all of them yield efficient parallel circuits according to this principle. Benefit of abstraction. So let's now generalize and extend the problem, however. So here the original problem asks for us to calculate the maximum or the general associative operations of all these n elements. And our next generalization is that the output should not be just one number, the maximum or sum of these all elements, but we also want to have a tuple of outputs. So tuple of inputs, n tuple of inputs, but also an n tuple of outputs. Namely, we want to calculate the partial maximum as well, not just all 16. This is the case when capital M is equal to n16, but also up to the first 15 only, and up to the first 14, and up to the first 13, and so on. So we want to do that for all, always starting at the left, but up to all possible end ranges, calculating the maximum or any other associative operation, so that the output is again an n tuple. And applications will be considered later when we discuss, for example, carry look-ahead adder of binary numbers. So let's continue this question. How can we solve this general problem? And this general problem is called, here you see the graphical illustration. So up to the first 15, up to the first 14, up to the first 13, and so on. And this generalized problem is called prefix sum, or sometimes it's also called scan. Now, let's try to extend our optimal circuit for the original problem with only one output here in the root to the problem where there are these n different outputs. And the naive way of doing that could be just to replicate our original circuit, but stripping it of the 16th element input, stripping it of the 15th element input. So repeating and copying our previous circuit n times, one for each possible value of capital M, one for each possible range. And having these n circuits execute in parallel results in, again, still a very efficient parallel circuit. Still, the depth will be the same because they operate in parallel, but now their size grows, right? So if we do it in that naive way, then the size becomes quadratic because now we have n independent circuits, each one for each different range, and each one of a linear size adding up together to quadratic size, which is not optimal. We now have a huge, namely a linear overhead. So let's think about this once again, and how can we improve that, still keeping logarithmic depth, but boiling down the size and maintaining linear size, although the output also now has n values. And the idea is, or the observation is, that actually we can reuse lots of the calculations. So for example, we already have calculated as part of this binary tree circuit, we've already calculated this range. So if now we want to add this range and this one to get only up to 15, then we don't need to calculate the sum over these ranges again, but only one here and one here and here. So we only need 3 additional gates on top of our circuit calculating all the range up to 16. We need only 3 additional gates to also obtain the range up to 15. And doing so repeatedly still results in a circuit of only logarithmic depth, because here 3 or more generally 4 is the logarithm of the number of elements. So doing that, additional kind of post-processing of the intermediate results produced by this binary tree still remains within depth log n. Now it's kind of like factor 2 times log n. But now we save a lot on the size, because as you observe, if we have calculated this range up to x12, then we can reuse that for, and these 2 gates that we've already kind of spent for also calculating the range up to x13. And similarly, if we want to have the range up to x12, we reuse this gate. And if you do the math and add this up, geometric sum and blah, 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 in the end, turns out that only a linear overhead, another plus n, suffices to calculate all the ranges individually, and not just the one range up to n, but all previous ranges. So this is the so-called parallel prefix algorithm or parallel prefix circuit that allows to calculate all these partial from left, always starting at the left, up to any possible position simultaneously, thus producing as output an n-tuple of results, not just one result in the root. So the result is a directed acyclic graph with n. So the leaves are here. These are kind of the sources, and with n sinks and sources. Good. So let's keep that in mind, because we're actually going to need that later for the carry look-ahead adder, which is going to have logarithm parallel running time and linear size, and thus be optimal. But for now, let's first consider another problem that we want to parallelize, and that's graph reachability. Let's specify graph reachability. The input is a graph, say a directed graph of n vertices, and 2 designated vertices S and T, the source and the target. And reachability problem asks, is it possible to reach the target from the source? Is the graph sufficiently connected? Does it have sufficiently many and sufficiently oriented edges to get from S to T at all? Yes or no? So it's a decision problem. And here we want to consider a strengthening variant of that, namely we have an additional parameter k. We're not asking whether one can reach T from S at all, but the question is, can we go from S to T within k steps at most k. Now, if we set k to be n, the number of vertices, then we recover, of course, the original problem. Can S be reached? Can we reach T from S at all. Whereas if we can reach t from s within n steps, or we cannot reach t from s within n steps, that's the same as saying whether t can be reached at all. Also, let me emphasize that the input graph is here. This specification is represented by an adjacency matrix, 0, 1 valued matrix, which says whether there exists an edge between any two given vertices in this matrix representation. So 1 means there exists an edge, and 0 means there's no edge. The vertices are numbered from 1 to n. So the output is the answer to the question, is t reachable from S within distance k? Now, this is a very classical graph problem, and how would you solve that sequentially? Probably using Dijkstra. And if you think about Dijkstra, how does Dijkstra proceed? Well, Dijkstra starts from S and then looks at all S is reachable from S in 0 steps. Then it marks all its neighbors, the neighbors of S that are reachable from S within 1 step. Then it looks at all the neighbors of those neighbors. These are reachable within 2 steps, and so on in waves propagating until having performed k stages in our setting. And if within that k stages t has been reached, then t is reachable within distance k. And other ways, Dijkstra will, in this case, just terminate, because we only want to know whether t is reachable from S within k steps. So this variant of Dijkstra will terminate after k rounds. Let's be generous and say Dijkstra has quadratic running time, and also observe that Dijkstra, yeah, that's the main message. Dijkstra doesn't really parallelize well because of these phases, right? Each phase really depends on and relies on the previous phase to be completed to have found which vertices can be reached within k steps, and then we can try to find the vertices that can be reached in the k plus first step additionally. So Dijkstra is not really suitable for parallelization. Instead, let's consider another approach. Let's try something else, namely a different way of solving the reachability problem in parallel. And that is based on linear algebra, actually. So you may or may not remember from discrete math that if we take the adjacency matrix and raise it to the kth power, then this reflects the connectivity of the original graph up to distance k. Let me say that again and illustrate that. So the original adjacency matrices says whether any two vertices can be reached in 1 step, whether there's an edge between any two vertices. The square of the adjacency matrix says whether any two vertices can be reached within 2 steps. So there's a entry 1 in A squared between two vertices, if and only if these two vertices can be reached within at most 2 steps. And similarly for A cubed, can the two vertices corresponding to this entry in the matrix A cubed be reached within at most 2 steps using the edges. And so, since we want to know whether t can be reached from S within k steps, the idea is to calculate the kth power of this adjacency matrix and then look at the entry in that matrix with index S and T, so row S and column T. Now this matrix multiplication or matrix power is to be understood as Boolean matrix power. Namely, we want the result to not be a matrix with integer entries, general integer entries, but with Boolean entries, since we start with Boolean entries 0, 1. So let's recall what is Boolean matrix product, n times n matrix product. Here's the formula that you probably know from linear algebra. So this is the row times column formula. where times refers to multiplication, and then take the sum. So that's a kind of inner product. But that's a traditional one. We're looking at Boolean matrix. So we replace multiplication with conjunction, meaning there's an edge from I to L, and there's an edge from L to J. That means there's also a two-step edge, two-step path from I to J. And we do that for every L, so any possible intermediate vertex, if there exists one, meaning a disjunction. So this is an n-ary Boolean disjunction. That's a Boolean matrix product of two Boolean matrices. Let's first try to devise an efficient parallel circuit for this Boolean matrix product. Now the conjunction part is easy because this is just one Boolean operation. So the depth of this is 1. And the size, yeah, let's get back to the size in just a minute, because now we have this huge disjunction. This is on a binary conjunction, binary, nothing to worry about, but n-ary disjunction. How can we do that? And here come in the observation that disjunction is an associative operation. So this is the case that we discussed initially when we generalized the maximum of n elements to the any n-ary associative operation, like in this case. And we saw that this can be calculated using a circuit of still optimal depth log n, right? So this becomes log n, but the size is now O of n, linear size, optimal. So this is an application of our abstract approach from previous slide, not yet the parallel prefix, because here we only have one range and not several ranges. But this is only one entry of the matrix or resulting matrix product. I mean the entry with indices I, j. We want to calculate the entire products matrix, so we want to do that for all possible values of I and all possible values of j, as in the row times column rule for multiplying two matrices, not just to get all entries in the resulting matrix. We do that for all possible values of the indices I and j by repeating the circuit, doing this for fixed I, j, and we have now several of these circuits operating in parallel simultaneously, which doesn't increase the depth, but does increase the size, because now we have n squared. Many of these circuits is of linear size, resulting in one big circuit of cubic size. So far, so good. So that's our n times n Boolean matrix product. But that's just one product. This is how we calculate a squared by multiplying a to itself in a Boolean matrix. Now, how do we get to the power a to the k? By repeatedly applying the squaring operation. So the first squaring, multiplying a to itself using this circuit, we arrive at a squared. Then multiplying a squared to itself, using a similar circuit again, a second time, we arrive at a quartic. Doing it again, a to the 8, and so on. After log k repetitions, we have arrived at the kth power of a. This is a sequential process. Log k times we apply this repeated squaring, each time using such a circuit of logarithmic depth and cubic size, but sequentially, each one after the other, so that the resulting circuit, the depth does grow from log n to log n times log k because of the k sequential repetitions. The size also grows. The size of one circuit is n cubed. repeating it, having log k copies, results in the size growing to n cubed log k. And that's our resulting algorithm for parallel graph reachability with depth log n times log k. In the worst case, when k is equal to n, that's a log squared n time parallel algorithm. And that is pretty efficient if you think about it. You might remember from chapter 1 where we talked about this table of computers of different clock speeds running different algorithms. But the fastest one was the computer with the slowest clock speed, 1 instruction every 10 seconds, running a logarithmic time algorithm. Now, this is a parallel algorithm, not with logarithmic running time, but with running time log n squared, which is still highly sublinear, still faster than algorithm with square root running time, faster than algorithm with linear running time. So this is highly efficient. And the size is, okay, let's be honest, n cube is a little bit more than we might want to have. We want as close as possible to linear size according to Brent's principle. But then again, yeah, it's still polynomial size. So to summarize, here we have devised logarithm squared time parallel algorithm, a circuit for parallel graph reachability. And as we're running out of time, let's take a break here and take a stock and summarize. So we've talked today, we talked about first parallel computation. We've classified different types of parallel computers, fine-grained on the one end of the spectrum and distributed computing on the other, with identified measures of algorithmic costs, namely depth for circuit-based parallel computation, span for distributed parallel computation as a way to reflect parallel running time, size as a measure of how large is the circuit, how much silicon basically does it cost us to realize that circuit using gates, or the work as a way of how much computing resources do we have to rent from the cloud, how many processors, and for how much running time. That's the work. And Brent's principle connects both the size and the work on the one end to the optimal sequential running time of a problem, not of an algorithm, but of a problem. And thus allows us to prove certain parallel algorithms to be optimal. Then we have started by devising and analyzing a circuit for the n-array maximum problem by expressing it as a sequence, as a circuit of binary maximums, so-called fan-in-2 circuit. We saw that this is optimal linear size and logarithmic depth. We've generalized that from maximum to arbitrary associative operations, such as logical disjunction, which was important at the end when we talked about the parallel graph reachability, where we would express Boolean matrix multiplication using n-array associative disjunction. And we would also use the repeated squaring. In between, we talked about the prefix sum problem, which is a generalization of the n-array maximum or n-array associative operation with one range to calculate all possible ranges, always starting at one, but ending at different endpoint ranges. And we saw that it is possible to calculate all these n ranges simultaneously, still in logarithmic depth and still in linear size. So next time, we're going to apply all these considerations, in particular the parallel prefix to the carry look ahead adder for adding binary numbers in parallel. If you think about it, your school method for adding long numbers, long addition, is inherently sequential. There's always a carry to be considered, possible carry, and that carry may go on from the least significant bit up to the most significant. So adding these numbers and following all the carries results in a intrinsically sequential algorithm, and the carry look ahead adder is a way of turning that into a highly efficient, namely logarithmic time parallel adder. And this carry look ahead adder makes heavy use of our generalization of the prefix sum method for associative operation. We will design and prove a certain operation on pairs of bits to be associative. And then our general theory says that there is an efficient parallel algorithm for computing all these prefix sums. So that's all for today. Thank you very much for your attention, and see you again with the second half of chapter 9 about the carry look ahead adder, and also we will be talking about sorting networks for sorting data in parallel in sublinear parallel time. That's all for today. Thank you and goodbye.